Good. Hello, welcome to this talk. We're going to talk about 5G, Edge, and Autoscaling. My name is Paul-André Raymond. I work at Beyond. I'm a Senior VP of Technology at Beyond. Beyond is a software company. We do AI-based software to manage large-scale telecommunication networks such as 5G and Edge network. And it's the topic of this talk today. And I wanted to have this talk because I wanted to convey my excitement about everything that's been going on in this industry. We've all heard recently all the hype around 5G and edge computing. And it's an exciting time to be working on these topics. There's a lot going on. There's a lot we've heard about in the last few days. And I wanted to give my perspective on it and also make it a little bit more specific, a little bit more concrete than some of the talks we've heard in the last few days. Well, my first point, the topic of the talk is really about showing how 5G and edge computing are driving new technologies such as autoscaling. And the first point I want to make is that really 5G and edge are coming. Unless you've been living on an island somewhere, you do know that those topics are driving the industry at the moment. They are very much hyped, very much talked about, but they are very much real. There's no going around each of them. They have real implications on how we need to manage the infrastructure. Of course, edge is at the top of the hype cycle at the moment, but it's also very, very real, and it will happen. So these two things go with each other, they feed on each other, and they have real concrete implication in how we manage our networks. So this is not business as usual at all. There's really something going on there. So that was the situation. That's the situation we are in today. These things are coming, but there's a complication. 5G is really about demand. 5G is really driving new usage in the network, being able to do more. Edge is also transformative. Edge is really about scale. It's really about putting a lot of devices out there in the network, being able to manage things in very many locations at the same time. And when you combine those two things, demand and scale, new usage, new demand, more, and more locations, it becomes extremely important to be able to do it, to manage the network in a very efficient way. The traditional methods, they don't work anymore. We need something more. And autoscaling is one example of that. It's by no means the only example of a technology that is implied by this transformation. It's just one example that I think is exciting, very important, and I wanted to tell more about it and make it go to the next step and make it a little bit more concrete and share with you some of the things that I am seeing in the industry at the moment. So this notion of high demand and high scale and large scale is something that we have a name for at Beyond. We call this, we have a vision for that. We call this the infinite network. And that's a concept, it's a vision, it's a lighthouse, it's a state of mind. And the vision is for a network that's available everywhere, all the time, for doing the things that we need it to do instantaneously. So it delivers the workloads that we need, where we need them, when we need them. It's not completely out of touch. It's actually pretty concrete when you think about it. And there are actually very real ways to deliver on these visions. There are ways to get there. There are technical approaches that will support the large scale that I'm talking about, but also variation in the demand that goes with it. And we can do that while controlling costs. And I want to tell you about three such techniques that we've identified and that enable this kind of architecture. Again, we only have 40 minutes on this talk. This is not an exhaustive list. I'm just going to give you three examples that are important and also drive on each other. So to drive the large amount of information, one of the things that we see emerging in this industry, and this first example is something that's emerging. Not all my examples are emerging. Some of them are things that are well in place. This one is something that's emerging. This is something that you hear more and more people talk about, and it sort of came out as a consensus in the last 3 months. There are other ways to do that, but this is the way that really we've heard about in the last couple of days from other people as well. So there's this architecture that's emerging where to manage a large number of edge clouds, we are building a hierarchical structure with a central node and possibly some regional nodes to do management and orchestration. And we've talked a lot about ONAP or ONAP-E to manage these edge clouds, which could be made of components that are OpenStack or Kubernetes at the moment. There could have been other ways to do that. Within the FogEdge group, we looked at peer-to-peer architecture for a while. We looked at architecture that were fully built on OpenStack and not dependent on ONAP. There could be federated architecture to be able to do things like that. But really, this specific architecture is emerging as a consensus that's being widely talked about. That's example one. Example two. So second technique that's being used at the moment is we are working on removing the man in the middle. There's a trend that emerged, this word autonomics, it was coined about 20 years ago. This is not something new, but it emerged from IBM and in the context of computer-controlled architecture. And the notion of autonomics is really about automation, but it goes one step beyond automation. It's not just being reactive and to a demand, it's also automation of the way a system or a network manages itself. And the concept of autonomics, may include things like self-configuration, self-healing, self-optimization, self-protection. You've heard some of those terms in the context of 5G with SON. It's really very similar concepts that build on each other. And autoscaling is one of the options, one of the things, one of the selves that we want to achieve. So it's part of that picture. And I want to point one more thing here is that in this architecture, usually this notion of autonomics, of self-management, there's a notion of a control loop. And there's been many ways to represent that control loop in the industry. The most common one is called the MAPE, monitor, analyze, plan, and execute. That's the one that's shown on this screen, or MAPE-K in this case, because this is based on a central knowledge base. So that's a very common way of representing it. You would see in other forums other ways of representing very similar loop. There are some that are called OODA, CADA, and others. But there's this notion of being able to monitor a system, build an action plan, and execute on that action plan, which is very important. And this notion is important because I'll come back to it when I talk about how to realize autoscaling in a little bit. So bear this diagram in mind. The third trend I want to talk about is something that's really close to my heart. And that's really the elephant in the room. That is the tool that everybody's talking about in all sorts of contexts. This AI and machine learning is really Also a major trend, not just in this industry, but across all industries. And it's not the same thing as the previous one. Autonomics is not AI. They build on each other. Autonomics is more the notion of it could be something that's purely reactive and policy-based and programmable, whereas AI and predictive analysis are more around the notion of learning and machine adapting itself to whatever demands it sees out there. So the reactive approach is slow. Here in this context, we are interested in AI and predictive analytics because it helps speed things up. So bear that in mind. I'll come back to it again later on in the talk as well. All right, so let's take a step back and talk about those two trends that I mentioned at the beginning. So 5G, edge computing are the two trends, and they drive and they have synergies with autoscaling, which is really the point of the talk. But before I go further on those trends, I want to tell you, I haven't told you yet, and I think it's important to bear in mind what I'm talking about when I'm talking about autoscaling. So let's take a step back and talk about it for a moment. In the context of a telecommunication network, autoscaling applies to, first and foremost, to user applications. You know, those are things like, those are microservices. Those are things like those facial recognition software that we may run on an edge node or in the cloud. This could be a Netflix application that runs in the cloud. They are workloads that are very often provided by third parties and run over the top of a telecom network. So that's one class of application. Second class of application is really the network functions. That's what we talk about when we talk about network function virtualizations and SDNs. Those are things those are devices that an operator used to have as physical device in its network in the past that are now transformed into virtual machines that will run as workload in the network. And those need autoscaling as well. And it applies. And then the third type of application that might benefit from autoscaling is really the management and orchestration software itself. The VIMs, the NFVM, the ONAP, and the MANO. Those are workloads as well. Those run on Kubernetes or on OpenStack, and those may need autoscaling as well. Autoscaling is important for all of them, but of course, you know, it's more exciting when we talk about user applications. Next slide. All right. So let me clarify. I know not everybody is a telecom expert in the room, so let's talk a little bit about 5G. You've heard a lot about 5G, and 5G is real. Operators are deploying it. It means that there's new spectrum being deployed, being used, so we can have more bandwidth for using our cell phones. It means that there are new services that will be available that work faster. Yeah, there's some broadband services, some low latency services like AR, VR, some IoT-based services like, which we often refer to in the standards as MMTC. And there are also features that comes in there. We might have heard about slicing. There was a talk about slicing recently. You may have heard about COPS, control and user plane separation, and edge computing, obviously. Those things come with 5G, and most people will tell you about that when they talk about 5G. But I think 5G is something much more important than that, much more transformative than that, and which people don't talk about, which you would not necessarily read if you read through the 5G standards. 5G is really about transforming, or with 5G, comes a transformation of the telco network into a cloud architecture. We finally are able to use a lot of the tools that have been used in the cloud in large data centers and apply them to manage a cellular network at scale. And that opens the door, in particular, to a software-defined network, to a network that can host payloads and applications from third parties. And it opens the door for a new monetization model for operators. And all of that is based on the cloud native concepts and the CI/CD concept. Now, why I insist on 5G? Because automation is important for 5G, and autoscaling in particular, as an example of automation, is very important for 5G. For instance, if we talk about network slicing, the concept of network slicing, which really is about dividing of the network, sounds pretty counterintuitive in terms of management of resources, unless we can actually have a dynamic boundaries between the slices. So being able to slice up or to scale up or scale down a particular slice is really central to the success of network slicing. Scaling is also important to be able to respond to demand from a large set of users. So slicing is really about demand from one corporate user or one class of users, but collective demand from many users may create a specific trend in the network. Maybe there's a sudden requirement on mobility. A lot of users are changing cells, and you need to scale up the mobility management features of your 5G network. So scaling is important there. And just as well as scaling might be important in response to some physical changes in the radio conditions of the network. So autoscaling is important for 5G. All right. How about edge computing? Well, there's been a lot of talk about edge computing. In this context, there are many definitions of edge computing in this industry. In this context, I'm really talking about edge computing as being able to bring compute to the edge of an operator's domain. So particular, that might mean in a 5G network to be able to deploy computing and storage resources at the bottom of a base station. So it is very similar to cloud computing, but there are also very significant differences to cloud computing. In particular, the scale of an edge node is much smaller than the scale of a data center. And the connectivity at an edge node to other nodes in the network is different. So some of those concepts are addressed in the white paper on edge computing that was published by the Foundation recently. So I'll refer you to that if you want to know more about the differences. But I want to make the point, one important point, that in the context of edge computing, automation and autoscaling is important, is extremely important. And the reason it is so important, of course autoscaling is important everywhere. We've seen it used in the cloud, we've seen it used by over-the-top players for quite some time. But the edge nodes are smaller, they are limited in resources. And the fewer resources you have to manage, the more intelligent you need to be in managing those resources efficiently. If you think of traditional demand and dimensioning curves, when dimensioning for a small scale, you actually need to over-provision a lot more the number of servers when you have few of them than when you are doing it on a large scale. So, the economies of scales are not there. So that's one aspect. There's another aspect why it's important to be really, really efficient when you manage workloads at the edge. It's the fact that you don't have just one edge node. You don't have just 10 edge nodes. You have thousands of edge nodes. So a small inefficiency in managing at the edge gets multiplied 1,000 times, 10,000 times, 100,000 times. A typical telco operator in the US has nearly 100,000 cell towers. So the potential number of edge nodes gets very large in the 5G context. So that's one relationship. Autoscaling is important at the edge because of efficiency. There's another relationship between autoscaling and edge computing, which I think is important, and I'll come back to it later on, is really coming back to the notion of control and the latency in the control loop. The shorter the latency in the control loop, the more efficient your control mechanism would be. And for that reason, autoscaling logic is much better placed at the edge and much more efficient when placed at the edge and not depending on a central office, which might be miles away or milliseconds away. And then, you know, the numbers I show on this slide are not scientific numbers. You would see, talking to different telcos, you would get different numbers. The ratio is, or the relationship between them is actually pretty stable. So I've seen numbers from different operators in the last few days, and they all look along these lines. Actually, those numbers are probably pretty conservative or pretty aggressive in the value. So by now, you might be convinced that autoscaling is important. Autoscaling is important for 5G networks. Autoscaling is important for edge computing. I'd like to talk now, change a little bit the direction of the discussion. I'd like to talk about some of the ways to actually implement autoscaling and some of the architectures that are emerging in that case, in that scenario, and the relationships between them. And so I'll go through a few examples, 3 or 4, and I'll compare them based on, you know, how effective they are in various respects. So my first option on how we would implement autoscaling, and I bring you back, so the diagram on this slide actually highlights, comes back to the architecture that I showed you at the beginning, my example 1, where we have a central hierarchical architecture on how to manage the network, and the autonomics loop that involves monitoring and analyzing and executing on an action plan for the control. And typically at the application layer, what you traditionally would see an over-the-top provider do is implement the analysis over the top. And this is real. This has been done. This has been done for many, many years. That's the way Netflix manages its network. That's the way most over-the-top players would actually manage their application and scale their applications. It works well. It is a good place to do your analysis because within the application, the developer of the application is actually the best person to understand the impact of an action would have on the usability of the application, you know, such as viewing a video. What's the impact of changing the codec if you need to change the codec? What's the impact of scaling up the research tools that you use to access your catalog, and so on. But this loop has limitations. The latency through this loop is very, very long, and the over-the-top applications, they have very little visibility of what actually is going on in the network. And this information of what is going on in the network is useful. It can help you anticipate what should be done at the control level. So option 2 is faster in this respect. Option 2 brings the analysis logic down at the central layer. This is what you would see. This is real too. This is what you would see people at ONAP talking about. This is a closed loop architecture that is being developed and, you know, has been deployed to some degree in some networks today. And it has many advantages. The latency is a little faster, and the central orchestration actually has visibility over a wide breadth of the network. So this type of loop is useful when you need to do things that involve many nodes in the network. You know, imagine a scenario, for instance, where you would have some mobility scenario. You know, a lot of the good example for automation really have to do with the failure scenario. So let's imagine, for instance, a busy highway. There's a traffic jam, an accident, or something happens. A lot of the cars are stopped, and people in their car, you know, they'd have nothing to do, car is stopped, so they pull up their cell phone, they start watching videos, watching the news, kids in the back are playing video games, and all of those things are putting a high demand on the network. A lot of data is being streamed down, and maybe some data is being sent up as well. Suddenly, and that puts a load on the cell in the network. Suddenly, traffic starts moving. You know, bottleneck is resolved, red light is turned green, or the accident goes away. All the cars start moving at the same time. All those cars that are receiving a lot of traffic start moving at the same time. They all would start handing over to the next cell or the next edge node at the same time, and suddenly you have to scale down the workloads on one node and scale up the workload on another node. Now, because of the central aspect of this option, it would be very good at doing that. But there's a third option that actually is a lot faster. So if actually all of my control loop is implemented at the edge, if my logic is implemented in the edge node, then the latency of the control loop is much faster. Then I have immediate access to all the information that's happening on the cell tower that's nearby, and we can deliver on a new kind of applications. I mean, this kind of scenario, this kind of high-speed scenario applies to what is called the ultra-reliable low-latency class of applications that are envisioned in the 5G standard. You know, imagine something like drone controls. If you have a number of drones, drones are really sensitive to, or a good example for control done from an edge node, because drones have a constraint on the power. They have constraint on how much weight you can put inside a drone. So it's a good idea to put the logic really in an edge node to control drones and help them manage themselves. So if you have a fleet of drones that's flying around and suddenly there's a failure, there's one of them that's falling, and all the other drones need to be rerouted at fast speed, well, then you need a very, very milliseconds are important in that scenario, and you need a very fast loop. And there are other examples, industrial applications, or that may require this fast loop. So 3 options. They're all important. They all have plus and minuses. And am I recommending one or the other? No, I'm not. Actually, I think all of them will coexist at the same time in the network. All of these things are needed. All of these things are being implemented today. And what really we need is a system to better coordinate their action. The challenge when you have, for those who have studied control theory, the challenge that we have when having multiple control loops is that you get some very, very complex scenarios of those interactions between those 3 loops, and coordination is needed between them. And you know, this is not new. It's been done. There's been research done around that. There was a very good paper by some people at INRIA who actually studied this very scenario and recommended some techniques to perform this coordination between the various control loops or the control logics at different level in the network. Now, it's research. What needs to be done at the moment is transform that research into actual implementation. And it's a little bit complex in our environment, because getting Vim level people to talk to master orchestrator people to talk to application level people, you know, there are some challenges there. But as a group, as an industry, we'll get there. And at a company like Beyond, we're actually building platforms that will actually enable us to do that. Second thing I want to tell you is that not only do we need coordination, but also there's a better way than the 3 options that I mentioned before. All 3 options that I mentioned, they all are reactive. They all adapt to they all observe a situation in the network and adapt to it. And that's a slow control loop. And in each of those scenarios, we can do better. We can do better by actually using AI and machine learning to predict what's going to happen in the network, to anticipate events before they actually happen. And just as I was telling you before, this prediction, this anticipation works at all three levels in the control loops, and it can be implemented in a platform such as the one we're building, and or the one that does the coordination that I was talking about a minute ago. All right, so that's my last slide. So in summary, recapping over my points, 5G and edge are things that are happening in the network. We need to cater to them, and they really drive the need for more intelligent ways of managing the network, and in particular for autoscaling. And this autoscaling logic is really best placed at the edge with a small control loop. And in that context, in the context of this multiple control loops that exist over the network, we really need a platform that will be able to coordinate and collect information from all the levels and predict, do predictive analytics for autoscaling. So that will bring the efficiencies that we need to actually build this network. That's my conclusion. I want to, there's a number of other talks also on the edge computing topic and autoscaling topics. I'm sure you've seen some of them. I encourage you, just before this one, there were a couple from the FUG Edge group, which I'm a member of and actually co-chair. And I encourage you to look at those, because they really show how some of these methodologies can be implemented, and that this notion of edge computing really can be realized in the network today. With that, I'd like to open it up for questions. There are microphones, and I think we have 10 more minutes.
Good talk. For the IoT, do you have an example or any comparison?
Any comparison?
Yeah, because you mentioned 5G.
Mm-hmm.
You mentioned some other verbal examples.
Yeah.
But for IoT, what are the limitations in terms of adopting a unified architecture?
Yeah, IoT is complex. The main complexity. Well, IoT is complex because there are so many different use cases. One use case that some people often talk about in IoT is surveillance, and this puts constraints on the network and a lot on the upstream link. And in that context, intelligent architecture can be very good at anticipating what's going on. So the same points would apply in that context.
Good.
Yes?
Yeah, could you, you mentioned ONAP. Actually,
Mm-hmm.
I'm very active in ONAP. We are developing a new architecture. For ONAP, the orchestration layer has to somehow manage the resources in the edge, yeah, by some way of really, some means, some tools. Mm-hmm. Do you have any insight into that?
Well, there's a number of projects. I mean, I'm sure you're aware there's a number of projects that are tackling how to do that, and some diverging projects. And on one hand, at the edge, you would use Crano or OpenStack or Kubernetes, ONAP as this multi-vim architecture that facilitates that. There's a lot going on at the moment, and how to do that and how to deploy a VM or a container on an edge node, how to move a container from one edge node to the next edge node, how to manage images and make them available in all the nodes and transfer them from one node to the next. All those complexities are there. And ONAP can have a central role in actually managing all of that. From a telco perspective, ONAP is a really great tool that's really a telco view, where you can actually, from a central place, manage everything that's going on throughout your nodes and your architecture.
As you said, we have a mediation or adaptation layer for multi-cloud.
Mm-hmm.
I was wondering if for the edge application or use cases, would you view any of those cloud providers, like a mini cloud provider, would fit into that model, or that's different?
It's a great question. It's a great question. When this notion of federation of mini clouds and multiple clouds that talk to each other, it brings all sorts of other complexities into the picture in terms of authentication, in terms of bringing up the architecture, and I don't think the tools are in place yet to do that. But that's the direction that eventually, as an industry, we will go into, especially for industrial applications. We have another question.
Right. Just to add to this, just to comment to your question, I think there are a couple of issues, right? So it could be an infrastructure error. Typically, we kind of monitor by our Nagios. And then if it is a VNF error, it's the DCAE, which is part of ONAP, like you said, that would monitor the VNF. Then we correlate the alarms, and then we try to do the closed loop.
That's my next question. Thank you. So the DCAE indeed is a critical part of the ONAP architecture.
Yeah.
DCAE stands for the data collection, analytics, and events. Mm-hmm. For edge use cases, your option 3, that you locally do all your cloud orchestration, it was option 3, yeah, or option 2? You mentioned that it would be more efficient if you do it through your edge cloud, yeah?
Yeah.
So this edge cloud, do you guarantee the service assurance is done within the cloud, or you rely on the higher layers?
Well, in this scenario, we're envisioning the service assurance done within that layer.
Yeah.
Now, it might be done at other layers as well, but here I'm proposing that it's more efficient if we do it within that layer. And DCAE does allow that, because there's this discussion going on at the moment where we can distribute the components of DCAE so that a lot of them live at the edge. And that's really why I have a regional Mano box on this picture, is to clarify that this control loop done at the edge could be done within ONAP, could be done within OpenStack as well, could be done within Kubernetes. But it's
maybe this is maybe we should have like a joint sessions. I don't know where and when. The DCAE today doesn't really touch into the detail of how you do that within the edge cloud.
Really?
Because the mediation layer, it basically, when you select the right VIM, the right infrastructure, then that's it. Then the infrastructure would take care of itself.
Okay.
So we want to close the gap there.
Okay. Okay, so there's some actions to take there.
Yeah.
All right. Well, there's work ahead, so that's good. Any other questions? All right. Well, thank you, everyone.